Kinetics is the study of particles in motion. Chemical kinetics treats a reaction as a collision between moving particles called reactants. As a result of these collisions, for a brief instance, two particles are in contact. In the previous video, linked below, we saw from the thermodynamic point of view that the stability of this intermediate is based upon its change in entropy. In the current video, we're going to look at the same state from a different point of view, based on the kinetic theory of gases. The kinetic theory of gases is developed dealing with perfect gases, meaning all the particles are moving independently, there are no attractions or repulsions or interactions with each other, and all collisions either with the container or with other particles are going to be elastic. So we'll start at first principles. We will just assume that there is some particle of mass m moving in the x direction, coming in contact with a wall occupying the yz plane. The force exerted by this particle is going to be mass times acceleration, where acceleration is the change in velocity with the change in time. If I look at the change in velocity, that's going to be the final velocity of the particle minus the initial. However, since the collisions are elastic, the final and initial velocities are going to be identical, so the change in velocity is simply going to be minus 2 times the initial velocity. Change in time can be determined through a little manipulation. The definition of velocity is the change in distance with the change in time. So the change in time is the change in distance over the velocity, where in this case, the particle traveled x forward and x backwards, so the change in distance was 2x. So my force, mass times the change in velocity with time, is going to be mass times minus 2 times the velocity with respect to time, which was 2x, or the force is equal to minus the mass times the velocity in the x direction squared, divided by the distance x. If I want to find out the pressure felt by the wall, two things. First of all, pressure is force divided by area. So in this case, the force is the mass times velocity squared over the distance. The wall has an area of y times z, so I get mass velocity squared over x times y times z, or mass times velocity squared over volume. One thing to note here is that the sign changed. If the particle is experiencing a negative force, it is losing energy. That must be transferred, so the pressure felt by the wall will be positive. So, for one particle moving in one direction, I have a pressure of mass times the velocity squared over the volume. If I expand this out to have that one particle moving in 3 dimensions, the total pressure is going to be the pressure in the x direction plus the y direction plus the z direction, which is proportional to the velocity in each direction. Actually, it's proportional to the velocity squared, and this is crucial because the velocity is a vector, so the square is simply the magnitude of the vector. So the total velocity is squared is equal to the x direction squared plus y squared plus z squared in magnitude, if not direction. The equipartition of energy says that each of these directions is equally probable, so each of them is 1/3 times the total velocity squared. So for one particle moving in 3 directions, 3 dimensions, the pressure is m times the velocity in the x times the velocity squared over 3 times the velocity. If I look for multiple particles, I simply have to multiply that by n, the number of particles I have. I do this for a reason. I now have, for a multi-particle system moving in 3 dimensions, a total pressure times n particles weighing m kilograms, velocity squared, over 3 times the volume. Or in other words, nmu squared over 3 is equal to pv, where since we're dealing with a perfect gas, that is also equal to nRT. Some manipulations. So the velocity squared is 3 times the number of moles divided by the particles times the kilogram is 1 over the molar mass. So I have the velocity squared of any given particle is roughly equal to 3RT times its molar mass, divided by its molar mass, rather. In actuality, since the flights aren't linear, the velocity of any given gas particle is equal to the square root of 8RT divided by 3m in kilograms per mole. This is significant. Velocity is meters per second. Mass is kilograms, temperature is Kelvin. Previously, R had been dealt with thermodynamically as 0.0821 liter atmosphere per mole degree Kelvin in the gas law. What R actually represents is the potential energy of 1 mole of independently moving particles, which is why it has one value. It's a universal constant, but can be expressed in 2 units. 1 mole of particles has a potential energy of 8.314 joules per mole degree Kelvin. So, I now know how fast a gas particle is moving. 2 things come out of this. First of all, not surprisingly, the velocity is proportional to the temperature by the square root. A higher temperature means more energy, means faster motion. So if I have the same molecule at 2 different temperatures, the velocity at temperature 2 over the temperature 1 is going to be the square root of the ratio of those 2 temperatures. Similarly, the velocity is inversely proportional to the mass. Given the same amount of energy, something heavier is going to be moving slower than something faster. So if I have 2 molecules at the same temperature, the velocity of B over A is going to be the square root of the mass of A over B. So 2 things come from this. Velocity is inversely proportional to mass, and velocity is inversely proportional to time. If you move faster, it takes less time to travel a given distance. Therefore, the mass of a particle is going to be directly proportional to how long that particle will take to move a given distance, all things being equal. This is known as a fusion. And a fusion experiment is a direct way to measure molar mass, and it occurs as follows. You have 2 identical cylinders with a pinhole on the end. One of them is filled with a heavy gas A. The other one is filled with a lighter gas B. In both cases, the piston has to travel the same distance x, and an equal force is exerted on both pistons. It's intuitive that with the same force applied, the heavier gas A is going to take longer to displace than the lighter gas B. This gives Graham's law of effusion, where you can directly measure molar mass, because the time of A divided by the time of B is the square root of the mass of B divided by the mass of A. This basic understanding of how particles move absent any other forces is the basis of what's called collision theory in kinetics. There are 3 major outcomes from collision theory. First of all, I have a given particle. What is the frequency of collision? How often will particle A collide with particle B? This is going to depend upon several things. First of all, how much space does A need to avoid a particle, to avoid a collision rather? If this is A and this is B, it's fairly easy to see that you need a minimum distance DAB, or the average diameter of A and B, in order for particle A to be able to pass between two molecules. In terms of space, pi r squared, the volume that would need would be radical 2 pi times DAB squared. If I'm looking purely at A collided with B, another important factor is how many B's are present to collide with. That would essentially be the volume density, or the number of particles B divided by V. Also, speed. If both particles are sitting still, no collisions will occur. What is the terminal velocity? How fast is A approaching B? Again, since velocity is a vector, that's going to be the square root of the velocity of A squared plus the velocity of B squared. So I get a collision frequency called ZA is equal to radical 2 pi times the collision diameter, DAB squared, times the terminal velocity, times the number of moles of molecules of B divided by the volume. Density. In total, how many collisions per second are there, A with B, B with A, per cubic meter? We already know how often A hits B. How often will A hit A simply depends upon how much A there is, the number of molecules of A over V. So ZAB, the collision density, is equal to the frequency times the density of A, or radical 2 pi DAB squared, terminal velocity, molecules of B, molecules of A, both of them divided by the volume, so divided by the volume squared. The third important thing, which will come up further along the line in collision theory, is what's known as the mean free path. Mean free path is sort of the inverse of frequency. Frequency tells you how often A will have a collision. Mean free path tells you how far can A travel without colliding with something. So very simply, the mean free path is calculated by dividing the velocity by the collision frequency. So I get the volume over radical 2 pi collision diameter squared over the number of molecules of B. That being said, if you compare that to the Clapeyron equation, which says the rate constant is equal to some pre-exponential term times e to the minus activation energy over RT, collision theory very simply says that the molecules collide to have a reaction. The rate of the reaction is proportional to how frequently they collide in a given volume. So you get the pre-exponential term in the Clapeyron equation being stated as simply being the collision density. The density of collisions between A and B will determine how fast A and B will react with each other. This appears to be a contradiction because there are two separate definitions that are trying to describe nature. Thermodynamically, you have the transition state theory, which says the pre-exponential term is related to the entropy of the transition state. Kinetics, on the other hand, deals with collisions, and you have collision theory, which says that the pre-exponential term A is equal to the collision density for the given reaction. It turns out that these two theories are not in conflict with each other. They just describe two different terms. The thermodynamic description, the transition state theory, fits the high concentration limit, because at a very high concentration, there are plenty of collisions, so the only thing limiting the rate of the reaction is the stability of the transition state. Collision theory, on the other hand, describes the low concentration limit. In this case, the transition state is a steady state. One molecule forms, one molecule dissociates. That does not change. So in a low concentration limit, the total number of collisions will determine the rate. This video concludes the discussion of the kinetics of chemical reactions. Future videos, linked below, will deal with the kinetics of specific types of reactions and specific types of systems beyond the simple reaction. I hope you found this video useful and that you will look at future videos. Okay, thank you very much and enjoy.